Hey, Sharina.
Okay, class, welcome to the fifth lecture on multibody dynamics. That is for this quarter the last lecture, and also homework assignment 5 is now available. The deadline is after a week from now, and the feedback deadline is then after 1 week after submission. I like to keep this strict schedule, otherwise people get confused, like, oh yeah, no, but maybe we get some more weeks, and then, oh no, but I forgot and I didn't. So we simply keep this scheme of homework assignment 1 week, and then after 1 week again the feedback closes. Homework 5 is not so difficult, it's not so much work. You're smiling, so that's good, but it, no, yeah, trust me, I'm a doctor. No, really, so it's not so much work, and it is sort of fun. It's all very doable. Okay, but before we start with contents, of course, we're gonna do Kahoot. Okay, Kahoot, where art thou? This sort of works, so Kahoot. There you are. Ta-ta. Play. There we are. Okay. Mm-hmm. And again, it's 5 questions, and I really encourage you to discuss with your neighbor. And discussing doesn't mean like saying it's green. That's not really a discussion. I mean, I've seen WhatsApp groups or other chats going by, and then blue, and then yeah, blue, and then that's not the whole purpose of the quiz, right? Ja. Gone, smiley gone. Moet ik clean-uppen? Waren er nog meer? Ergens. Oh. Heeft zichzelf eruit gegooid, denk ik. Ja. Nou. Yeah. Come on, guys. Yeah, beep it up. I can do that. Okay. Ja. Let's start, right? The missing word. I mean, I spent so much time on this advertisement. Yeah, okay. Point, yeah, it's some archaic French word for non or no figures. And no figures will be found in this book. Yeah? Oh, very good. The constraint force. Yeah, again. Not without reason.
Min 1, want die ei aan de andere kant natuurlijk. Ja, dus het is geel. Toch? Ja, anders had je iets wat ik een ei voor
Oh, je moet gewoon de Jacobi. Nee, is dat niet.
Oh, zo, ja.
Maar dat kan toch niet. Ja,
niet zo uitwillen. Nee, voor mij zijn
ja. Ja, okay. So that works well, thank you. Again, the front row, I guess. Yeah. Something on potential energy in the spring, but beware, everything is non-linear, so
natuurlijk moet je doen over de lengte dan. Dus relatief over de L. Zesde. Ja. Sorry. Is dat
ik ben verkeerd zet gezegd.
Nee, ik moet maar. Je moet gewoon Unity checken. Unity checken. Precies. Ja.
yeah, okay, very good. Again, front row. This takes some more hard thinking.
Heb je niet heel veel? Omdat je dan als je massa niet beweegt, dat is ook niet
Ja, voor zero motion.
Het is niet rood. Het is ook niet blauw. Ja. Ja, wat is het verschil? Heb je niet een noodwerk? Nee, ja, een noodwerk. In principe kan je hoofd ook bewegen.
Je kan het karretje bewegend hebben en massa stil. Maar
ja, S kan ook sowieso. Die schoot ook. Oké, doen we dat goed?
ja, groen.
Heb ik dat geklikt of niet? Ik heb het laatst geklikt.
Ik ook.
Oh, ik had toch verkeerd gegoten.
Okay, so this asks for some feedback. So the first feedback is that the answer is in the book. I mean, the chapter I talked about, this problem is well described as an example in the book. So I put it in the quiz as a sort of an incentive for you. Oh, next time maybe better to read the book, right? Okay, so that's the first statement. Then the second one is, what is going on in this problem? Well, if you look at the equation of motion, I'm talking about not finding a solution. And that can only happen when this mass matrix is singular. And that can only happen when the determinant of this guy is singular, and that is when you calculate that that's the case when cosine A is 1, or in the case where we have the angle vertical down or vertical up, and all the other repetitive cases. So what is going on when the mass is vertical down? Well, the problem is that I can have a finite velocity distribution in the system, whereas the mass does not move. Bear with me, I will talk about it maybe later during the lecture also. If the thing is hanging down, I can have a speed in this direction and also an angular speed of the bar such that this point is just stationary, it's not moving. And then you have the crazy situation that you have a finite speed, but that there is no mass coupled to that speed, or in otherwise you have a finite speed and zero kinetic energy. Well, that cannot be the case. Then that's an unsolvable problem. It's in the book, there are some pictures with it and some explanation. Okay, this was number 4, eh? Last question. It should be an easy one, eh? If I... TMT method finds its origin in... It is. It is. I mean, this is a... Yeah, okay, very good. Well, rood in a sense is correct because this is a bar in Rotterdam, I mean, but the method was not developed there. Okay, that was it. We're done. Please give your feedback while I'll get the results. Okie dokie. Okay, thank you. That was the Kahoot. Then we go down with this one. Yeah, and then we're gonna talk about some contents today. So the topic for today is again these generalized independent coordinates, but now instead of using the Lagrangian method, we are going to use a different method, which is a combination of virtual power and D'Alembert forces. And by some strange way, it's called the TMT methods. It's not my name. Somebody started in this faculty talking about it like that, and then it stuck. I mean, that's how things go. But I think the main thing is virtual power and D'Alembert forces. So again, we start from our virtual power expression. So the virtual power for that system, and everything expressed in the center of mass forces, and then of course the D'Alembert forces at the center of mass times the virtual velocities of the center of masses. And so these are all our variables in our system initially, and this is 1 through 3n. If we have n bodies, then we have 3n coordinates and 3n applied forces. Now let's be specific. All these coordinates are x1, y1, phi1, x2, y2, and then and then the last one is phi n. And likewise, these forces, again at the center of mass, force in the x direction, those are the applied forces. And then the missing term is, of course, what is this mass matrix? Well, in our case, it's a very simple one. It's a diagonal matrix, and you start with m1, m1, i1, and then you get m2, m2, i2, etc., until you end with in. Okay, so these are all the elements up till now for this constraint system. And the next step, we're not going to express the constraints, but we're going to find ourselves again a set of generalized coordinates which uniquely describe the system. So let's be specific. In our double pendulum case, if this is the double pendulum, then we have these two bodies here, body 1 and body 2. So then the number of coordinates, I runs from 1 to 6, so we have 6 coordinates. We do know that we have like 4 constraints on the system, so 4 constraints, meaning that we have 6 minus 4 is 2 degrees of freedom. So now we have to make our choice. And what did I do last week? I think I took one absolute and one relative coordinate. So let's today do something else. We take one absolute angle here, and again the absolute angle beta here. I mean, that's just to show that what you take as generalized coordinates is your choice. As long as it uniquely describes the configuration of the system, it's okay. Yeah.
How are you sure that it will create a unique solution?
I'm not.
Are you not?
No. Well, in this case, I have the experience that they are okay. So you're never sure. You can check in various ways, but there's no definite way to check it actually. Even if you do computer algebra and you write the expression, you say, oh, give me the inverse, probably the whole thing will collapse and it will not find a solution. So. Okay, so for now I'm choosing these alpha beta things. And as we have seen in the Lagrange equation, it's essential that we are able to express these CM coordinates into our generalized coordinates. So these are our generalized coordinates. So we need some expression. So express the COM xi's in the QJs, the generalized coordinates. That's what we have to do. So symbolically you could say, oh, xi is some function, and now I explicitly call this function, give it a name, and I call it ti of qj. Should be a j. And so this is not kinetic energy, but it's the t from t time. No, it's a t from transformation. Huh? It's transforming these generalized coordinates into our center of mass coordinates. So it's from transformation. Transformation. That is the keyword. That's the t from. Okay. Now, given this t, we are now able to do the whole kinematics in terms of our generalized coordinate speeds and accelerations. And that's just a matter of differentiating the stuff. So if we want to know the speeds of everything, or the speeds is not nice. Actually, you should say velocities. So velocities. So for the velocities, what do? You just differentiate. So we get x dot I is ti, comma j q dot j. So now we have a nice expression for our, and to make it totally complete, you say I runs from 1 to 6 and j runs from 1 to 2. Those things are necessary if you do coding, because then you have to know how do the loops have to run. Virtual velocities, we probably need them, because here, remember, here in this virtual power expression, we have virtual velocities. Well, virtual velocities, you can use any symbol, an asterisk, a v sub, some magical thing, but people for some reason like virtual velocities with this delta. It has nothing to do with differentiation. Nothing. Nothing, Mr. Faulty. Nothing. I know nothing. Okay, so it's virtual velocities. And then on the other side, we also have virtual velocities. And again, the same ranges. Now, how about the accelerations? Well, differentiate again, right? And now I keep this first constant and I first differentiate this, and then I'm going to differentiate this guy, because we have these two terms, so you always have to do one times the other and the other time. The chain rule, I think it's called the chain rule. So q double dot, to time, that's very simple. And now I have to differentiate this with respect to time, and I can't. I first have to differentiate it with respect to the coordinate, and then the coordinate to time. So I get ti, comma jk. I had my q dot k, and then j, and this one. So we see two terms in these accelerations, and what are they? Well, first of all, it's nice to see that this Jacobian in the accelerations, from this acceleration to this acceleration, is exactly the same Jacobian as here. And it's exactly the same Jacobian as in these virtual velocities. That Jacobian always stays the same. So that is, this Jacobian is sort of a fundamental mapping, as we will see later on. Then then accelerations are two terms, this linear part and this part, linear in the accelerations, and this is quadratic in the velocities. Now, we have a tendency, or I have a tendency, to call these convective terms. And I think it comes from fluid dynamics. I think they also use the thing convective terms there. And what do I mean? Well, these are all the terms with alpha dot squared L, or V relative alpha dot. Yeah, those kind of terms. So centrifugal forces, what is this, Coriolis things and so on. All these accelerations which have to do, not that the magnitude of something is changing, but the direction. So you have some velocity, and then the direction of the velocity is changing with a certain speed, and then you get these terms. Okay. If we have introduced, well, we have introduced these new or extra, or yeah, let's say extra coordinates, right? The generalized coordinates. Now, if you introduce generalized coordinates, you automatically, for free, get generalized forces. Then we get, for free, generalized forces. And the symbol I like to use is capital QJ. And then how are they defined? Well, they are defined via the power definition. So we say by definition power is equal to QJ Q dot J. So whatever thing, physical thing you choose for your generalized coordinate, it has immediately an effect on the definition of your generalized force. So in a very simple case, suppose your Q has the dimension of meters per second, just a normal velocity. Well, then we know that power is work per second, per time unit. Work per time unit, that's power. Then if I have here meter per second, then by definition apparently this guy is Newton. Okay. It seems very obvious. If a linear thing is some speed thing, then the force is just a normal force. But now let's do crazy and say, well, our generalized coordinate is an angle times a distance. So alpha times L, something like that. Then what is the unit? Oh, again meter per second. Well, so nothing changes. Now let's say our generalized coordinate is alpha to the power 3. And you may think, why is he taking that as a generalized coordinate? Well, sometimes it's useful. Sometimes in a problem it's useful to take the third power of some quantity in the system, say, hey, that is my coordinate. Maybe because it's an invariant in some cases or whatever. Doesn't matter. So meaning that Q dot is then some alpha squared times alpha dot. And that automatically then defines, if we take in units, then we have here radians squared, and then this is radians per second. And then here we have to have Newton meter per second. And that means, and radians is of course nothing, apparently that Newton meter is our unit. Yeah. Now, say you have some distance, as a coordinate, some distance squared, s squared. Then the velocity of the thing is s times s dot, so that's meter squared per second, right? Okay. And now it's becoming strange, because this should be Newton meter per second. Here we have meter squared per second, so this should be in s. Then the unit here is Newton per meter. Okay. Well, that's how it is. Then your generalized force is the physical quantity of Newton per meter. Okay, so small intermezzo about these generalized forces. Yeah.
What if your generalized coordinates is not just one, has not one unit? So you have the distance and an angle.
Yeah.
Do you then also have a generalized force that has multiple units?
Yeah. So in the audience one said, suppose your generalized coordinates is the distance s plus an angle. Well, the problem in mechanics is you cannot add apples with pears.
This is not what I meant. So
oh.
Say you, for the 2-bar problem, you take an angle alpha and a
no problem. I mean, this is for one coordinate, so QJ. Okay. So for any coordinate, you get then any other type of generalized force. Yeah? Okay, clear. Okay, so those are the forces. So we have generalized coordinates, we get for free our generalized forces, and that means then that the virtual power expression we have to enlarge, because if we have more forces and more coordinates, then we have more power. So we put an asterisk there and we say originally the thing we had were all these applied forces at the center of mass times virtual velocities, what is it, I, yeah. But now we have to add, of course, the virtual power of our generalized forces, which is simply this. Now the statement is that this is 0 for all virtual velocities which are not equal to 0, then the system is in dynamic equilibrium. And that's what we want, because the dynamic equilibrium is actually the equation of motion we are seeking. But we are seeking it in terms of these guys and not in the terms of the CM guys. But that's peanuts actually, because you just have to substitute the virtual velocities expressed in the virtual velocity of the generalized coordinates, and you just have to substitute here the expression for the acceleration in terms of the virtual, in terms of the generalized coordinate acceleration and velocities, and then that's all. And the rest is history. I mean, you just have to put it in the equation and add and subtract and get your signs right. So let's do that. So again, we have this delta P star. Then we have these forces, Mij. Now I have to substitute the whole expression for these acceleration of the center of mass expressed in the generalized coordinates. So Ti, and sometimes I change coordinates, which we call dead coordinates, because I already have some variables like this. I use a k here, and then plus convective terms KL, Q dot K, Q dot L. So those are these accelerations, right? Then I have to multiply with the virtual velocities, but I want to express them in terms of the generalized coordinate virtual velocity. So again, I put in this mapping T, I, comma, J, delta, Q dot J. Substitute this for this. And then we have plus Q, J, delta. And this should hold then for all these, as long as they're not all 0. And it's now nice because we have everything expressed in variations of these generalized coordinates. And then we just have to add up all this stuff, and then since it is for arbitrary generalized virtual velocities, and we have J of these, finally we get J equations. And how does that work? You first assume, well, let's assume I have velocities of 1, 0, 0, 0, 0. And then you say, oh, that's the first equation. No, I assume 0, 1, 0, 0, 0. Oh, that's the second equation. And then you walk through the whole thing. Oh yeah, I have J equations. So the result is J equations of motion. And what do they look like? Well, I'm going to push this to the front side. It looks a bit more. So I write Ti, comma J times this Fi minus this Mij, then the square bracket Ti k, Q double dot k, plus these extra terms Ti k L, Q dot k, Q dot L, close the bracket, and then we have plus Qj equals 0. It just fits on the screen, right? Now, yes, this is the equation of motion, but we are used to writing it as mass times acceleration is forces. So that's what we're going to do. We're going to shuffle everything until we get mass times acceleration is forces. So how do we pull out mass times acceleration? Well, I see here a mapping which goes in front of this. Here's the mass, here's the acceleration. So the first thing I need this term times this term times this term times this. That's the first part. And that's my mass times acceleration. So I get Ti, comma J times this Mij. This should be a J, sorry. Times, and yeah, that is not very nice. Oh, what did I do here? Tij, yeah, it's I didn't do it very nicely with all the indices. I should correct myself, right? Let me see, how can I correct myself? That is a J, that is an I. The problem I have is I use inside here a J and also on the outside here a J. And that sort of breaks up the whole stuff. Okay, let me get back. Delete this. Yeah. This J, here we need a J. Oh, I need my pen here. Yeah. Okay, so that is done. Then, since I want to keep on the outside a J, Ti, comma J, I get the Mi, I make a K out of this, then I get Tk, comma L, Q double dot L. I'm allowed to do that because all these indices are inner indices, they're dead. So this is the first part. This is my mass, my mass times acceleration. That's my first part. Now there's a minus sign here, meaning that this stuff is all actually on the other side of the equation. So actually we flip the whole equation. So now on the right side here I'm going to write, of course, first my Qj. These are just the generalized forces. And then what remains is this part and this part. So remaining are plus, then we have this Jacobian, Tij again, times Fi, these applied forces. And then there's a term minus Mij times d's convective acceleration. And I have sometimes a tendency to call these guys Hj. Because I hate to write all these long expressions. So then I write minus M I K H K. Then maybe we put brackets around this to make it more clear. And then the thing is done. Then here we have our equation of motion. And then you can add, of course, maybe HK is Tk Lm Q dot L Q dot M. It's not so, these are just convective accelerations, known terms. We call this method the TMT method. Well, it's now clear why it's called the TMT method, right? Because you just read here these product of these matrices. So these matrices transform the mass matrix in a sense. And what do they do with the mass matrix? They sort of make it more compact. We go from a high dimension, 6, to a low dimension, 2 in this case. So it really is like a projection on the whole thing. So that is actually the whole math behind it. Now, in there is also a sort of a matrix vector mixed notation, and that is the following. So until now we worked with these indices. Now you can associate that with a matrix, and then the matrix goes like this: Ti, j. So this is the matrix, right? Really the thing you have in MATLAB with the row and column numbers. And not Tji, but Tij. So rows and columns are well defined what they are. Likewise, we can also say that this index symbol Mij, I'm going to associate that with a matrix M, I, j. Very straightforward. The problem is, of course, with this thing, you cannot associate that with a matrix because you have 3 indices. So therefore, I like to write this H thing. So this H term, this HK, which is Tk Lm Q dot L Q dot M, I'm going to associate that with a vector HK. Just to So what do I have done? I have the matrix, I have these transformations. Yeah, well, this is obvious, I think. Well, you can say the Qj, I'm going to associate that with a vector, Qj, there, no. Very thrilling thing. And the Fi, I'm going to associate that with a force, also single index. So now I have all my matrix symbols, and now I can write the whole thing as a matrix vector equation, and it goes like this. So then we have this transformation matrix times the mass matrix times the transformation matrix. Then I have Q double dot, this vector, equals the vector of these generalized forces plus this transformation matrix times the forces minus the mass matrix times these convective forces. Now this is then our TMT method in a simple matrix vector form, although there is one thing which is not correct. If you look at this multiplication, then you see, oh yeah, that's MIK times TKL. So that's a real regular matrix multiplication, right? But now look at this guy, Tij Mik. That doesn't fit. Then, because the first index, you then have to add with this first index. And it should be the second index. Otherwise it's no matrix multiplication. Now we can fix that by taking the transpose of the matrix, right? Then it's completely in accordance with what's stated here. And likewise, if you read here, it is the first index which is the I, so that means again you need the transpose of the matrix there. And that should be yeah, the correct thing. Let's compare this to Lagrange equation, right? Well, no, one in between step. I'm going to associate this expression T transpose MT with a matrix M bar. It is a mass matrix, some transport mass matrix. And I'm going to associate these forces, Q plus T transpose times F minus MH. I'm going to associate that with a force Q bar. I mean, these are all forces, right? This is a force transformed. This is convective acceleration times the mass is a force transformed. Everything is forces. And everything lives in this generalized force dimensional world. And if we do these substitutions, then finally we get the following equation: M bar times Q double dot equals Q bar. Or in other words, by using generalized coordinates, we are still doing, of course, Newton. We are still doing some of the forces is mass times acceleration. Nothing changed there. It's only that the variables we use are more compact, or it's still simple. Force is mass times acceleration. Sum of the forces is mass times acceleration. Nothing changed. Then compare this with Lagrange. So what does Lagrange say? How do we get the equation of motion? Well, first you have to do a trick. You have to start from your velocities and your coordinates, and you have to go up one level and go to energy. So in Lagrange you have to take this Newton equation, and then you multiply it with speed and time, and then you integrate that. That's the first step you have to do. Why? Well, to get things like kinetic energy and potential energy, right? Then, if you have these guys, then how do you get the equation of motion? Well, you take the partial derivative of the kinetic energy with respect to the speed, and you do that with respect to time, minus, and that's too much work you did, so then you have to subtract this one, and then you add this guy, and then you say that is the applied generalized forces. Yeah.
Why exactly do you do too much work?
Remember, in the derivation, we had to pull something into this differentiation, and then we said, oh, we differentiate too much, so we have to subtract this. It's always pretty magic, like where does this term come from? So look in last week in the derivation of the Lagrange equation, you see we need this extra term. Otherwise we do too much work here. Because we pulled some Jacobian in the bracket, meaning that we put a little bit too much work in there. Anyway, now we have this, so we have this, this is to get the equation of motion, but watch what happens if we compare this with this method. What do we do in Lagrange? If we say you have two levels, you have a Newtonian level, a Newtonian world, where you say, oh, I have forces, I have speeds, I have accelerations, and then you also have one higher up level, which you reach by multiplying with speed and time and integrating, and that's what we call the energy level. So you start from a Newtonian level for Lagrange, then you go up to an energy level to get your energy expressions, and then you differentiate again to get back to your level of forces. Because in the end, of course, whatever method you apply, you want to have your force equation. So that is what Lagrange does. This is Lagrange. And what does the TMT method do? Well, it stays on the level of forces. There is no energy concept, we do not have to integrate stuff. We just take some mappings and we project everything on our generalized coordinates, and that's it. That's the big difference. And homework 5 is about seeing what the difference is if you use that method. 10 seconds to go. Oh, let's say we'll take coffee, right? Break.